Chapter 2.1, the derivative and tangent line problem, day 3. We're going to start with that problem I hinted to yesterday. Find an equation of the tangent line to the graph of f at the indicated point. We're just doing that part of this problem. All right, so first off, I said we'd use the alternate definition of derivative, which means f prime of c equals the limit as x approaches c of f of x minus f of c all over x minus c. Now in this case, c is 0 because we want the x values. So we'll find f prime, the derivative at 0, equals the limit as x approaches 0. F of x is 1 over x plus 1 minus f of 0 is 1 over x. Okay, complex fraction. We want to multiply both sides by the, or top and bottom by the denominator, which is x plus 1. So we got the limit as x approaches 0. We'll distribute to the top. X plus 1 cancels initially, 1 minus. X plus 1 will distribute the negative right away to be negative x minus 1 all over x times x plus 1. Taking a look, 1 minus 1 is 0. We got x in the numerator and the denominator. Those cancel. We're left with negative 1 up top. X plus 1 on the bottom. If I substitute in 0, f prime of 0 is 1 over 0 plus 1, or negative 1. So the slope of the tangent line is negative 1. Now we want to find an equation of the tangent line. An equation of the line, the best way to do this is to use what's called point slope form. Y minus y sub 0 equals slope times x minus x sub 0. Let's do this on a clean page. I'm going to copy my slope over. My point is 0, 1. All right. So again, slope, point slope form, y minus y sub 0, which means y minus a y point, equals slope times x minus x sub 0. For the AP test, when they want the slope of the tangent line, or they want the equation of the tangent line, you find slope, you have a point, you plug them into point slope form, and you're done. You do not need to solve for y. You can just leave it like this. This is the slope of our tangent line. Find the tangent line. Find the equation of the tangent line to f of x equals 2 over x at x equals 3. So same thing. Let's find f prime of 3. That'd be the limit as x approaches 3 of f of x, which is 2 over x, minus f of 3, which is 2/3, over x minus 3. Plug 3 in. We should always try plug and chug. It's never going to work for derivatives. You have to do some work. We will multiply top and bottom by 3x. All right. On the top, as we distribute it, f prime of 3 equals the limit as x approaches 3. Distribute the top, the x's cancel. We got 6 minus. Distribute the bottom, distribute 3x times 3. The 3's cancel. 2 times x is 2x over x minus 3 times 3x. 6 and 2 have 2 in common, so I'm going to factor out the 2. So we got 2 times 3 minus x over x minus 3 times 3x. These are almost the same. They would be the same if we multiplied 1 by negative 1. So I'm going to factor it out. So that's negative 1. It'll cancel. And what we're left with, f prime of 3 is negative 2 over, let the bottom approach 3. 3 times 3 is 9. So the derivative is negative 2/9. All we need is a point now. Well, x equals 3. We just need y. If you know y, how do you find x? Let's put that into the function. F of 3 is 2/3. So the slope, or the equation of our tangent line, point slope form, y minus y sub 0 equals slope times x minus x sub 0. Plug those in. Y sub 0 is 2/3. Our slope is negative 2/9. And our x value is 3. So the equation of our tangent line without simplification is y minus 2/3 equals negative 2/9 times x minus 3. Find the equation of the normal line, okay? Normal just means perpendicular, all right? So to do this, to find the equation of the normal line, what we do is we find the derivative and make perpendicular. Okay, so all we're going to do is we're going to do the same thing, just when we're done we need to use the perpendicular. Negative 1 over the reciprocal. All right, so we'll start. F prime of 4 equals the limit as x approaches 4. We'll do f of x, square root of x plus 1, minus f of 4, square root of 4 is 2 plus 1. 2 plus 1 is 3 over x minus 4. We'll continue. Clean up the top a little bit. Square root of x minus 2 over x minus 4. Radicals, so we need to rationalize. We'll use the conjugate of the top on the top and bottom. So we get the limit as x approaches 4. We get x minus 4 up top, x minus 4, square root of x plus 2 on the bottom. These cancel. We're left with 1 up top, square root of x plus 2 on the bottom. When we substitute f prime of 4, we get 1 over 4. So we got our point, or we got our slope, we got our x value, our y value, f of 4 equals 3. So our tangent line, or more specifically our normal line, is going to be the same equation type. Y minus y sub 0, slope times x minus x sub 0. Be the same idea, so y minus, or y sub 0 is 3. Slope of our tangent line is 1/4. Our normal line will negate, and reciprocal is negative 4. X minus 4. All right. And I kind of alluded to this yesterday. The derivative doesn't exist if we have a sharp turn. And the sharp turn, because we need to have left and right approach the same value. So here's the alternate definitions for left and right derivatives. And these are used more specifically for piecewise functions. So we can make sure left and the right piece both approach the same value. Well, let's take a look at an example here. Here's a piecewise function. Does the derivative exist at 0? So what we need to do is find the derivative from the left and the derivative to the right and just see, are they the same? So we'll do the derivative from the left first. Now, because the left is linear, you should easily be able to calculate the derivative. What is the slope of this function? Well, it's 3. No, that's the left derivative. The right derivative, the limit as x approaches 0 from the right, we'll go f of x, which is x squared plus x minus 6, minus f of 0. If we put 0 into that function, we get negative 6, all over x minus 0. All right, we got a little simplification already done for us. That can cancel. These x's have x in common, so we'll factor those out. We got the limit as x approaches 0 from the right. We got x plus 1 over x. Cancel there. We got x plus 1 as that approaches 0. As that approaches 0, the derivative approaches 1. So we can see the derivative as we approach from the left is 3. The derivative as we approach from the right is 1. So does the derivative exist at 0? No. We have that sharp turn, which mathematically we call it a cusp. Okay? If we look at another example, it's the same idea. The left derivative, the derivatives that we approach from the left, as we approach 1 from the left, and again, this is linear, so what's the slope of that? Is 1. As we approach from the right, we'll do f of x, x squared plus x plus 3, minus, okay, f of 1. 1 plus 1 plus 3 is 5, all over x minus 1. You can try and plug and chug. If you've done it right, it won't work. The derivatives never work with an initial plug and chug. So what we're left with is x squared plus x minus 2 over x minus 1. If we factor that, as x approaches 1 from the right, we got x plus 2, x minus 1 over x minus 1. These cancel. We got x plus 2. We do a plug and chug. We find that the right hand, the derivative, approaches 3. All right, so in review, the derivative finds the slope of the tangent line. A lot of people substitute that or simplify that down to say the derivative finds the slope. The derivative does not exist in 3 situations. When the function is not continuous, when there is a sharp turn or a cusp, like we saw in those last 2 examples, or if it's a vertical derivative or vertical slope.